right, so the next little section I want to look at in chapter 10 is dealing with the structures and classes of alcohols. We'll talk about some physical properties, acidity, oxidation, and that'll segue in perfectly into looking at some reactions. So let's take a look here first at, go ahead and put an S there, structure and classes of alcohols. So a lot of this is just review, right? We know that the hydroxy or hydroxyl group is sp3 hybridized. It's got two sets of lone pairs on it, right? And this is our H bond. We'll see that that affects some of our physical properties too. And the environment of the carbon that's attached to that OH, this guy, dictates whether or not we have a methyl, primary, secondary, or tertiary alcohol. So let's look at some examples. So a methyl is an OH group connected to a carbon that has no other R groups on it. So that carbon by itself is just connected to 3 H's. Right? This carbon here is connected to our OH. It's connected to just one R group. So that is one carbon atom. And that's what makes this primary. Right, same deal over here. If we look at this guy, same analysis. That's a carbon here. Right? Over here, got another. So 2 carbons, secondary. And then you can see where I'm going with this, right? 1, 2, 3, tertiary. And there you have it. So we need to understand this terminology because it's used in the vocabulary of this chapter and in the next chapter. Now, some of the physical properties that we see with alcohols are reflected in their boiling points, right? And that's because of H bonding. So if you look at this little kind of chart that we put in here, you have propane, which is governed by London dispersion forces, boiling point of -42. Right? So you come over here, molar mass changes a little bit here, right? Not by much though, but you throw in oxygen, it gives you a dipole, boiling point increases from -42 to -25. Right? And if we just come over here and get some H bonding, we went up 100 degrees. Right? From -25 to 78, it's more than 100, right? 103. Anyway, this is responsible because of the H bonding that we get right there. Okay, so we know that kind of from our lab and stuff that we learned earlier this semester. Now, the other thing that I want to spend a little bit of time talking to you guys about is the acidity of alcohols. So the big important note right here is this, and let's just put like a caution right around there. And note that the acidity of these compounds, these alcohols, is governed largely by the ease of solvation of the oxide. Now the pKa's range from about 15 to 19, and it turns out that larger carbon groups on the alcohols make the alcohols less acidic. Well, let's see if we can explain why that is. So if we look down below here, we can see that there's two reactions that I've written out for you guys. And here we have pKa's, right? We have the pKa of this alcohol. This, by the way, is a primary alcohol, right? You guys remember here? It's a tertiary alcohol. When we add these to water, you have the potential to form in this acid-base reaction a molecule that has a minus charge on it, right, and another one with a minus charge. So let's zoom in and let's talk about these two guys in a little bit more detail. So this molecule really kind of has two parts to it. So it's got this part right here, right? That part of the molecule is very polar, right? It's got a negative charge. And then it has this part of the molecule. That part of the molecule, molecule is non-polar and we'll say this, nonpolar part. So this part of the molecule down here is simply a nonpolar part. Now, we're in the presence of water, right? So water's going to come over here and solvate this guy. And it can solvate that pretty easily because this big nonpolar part can get out of the way. So what we can say over here on the side is this. We can make a general statement. We can say, well, that end is easier to solvate, right, with water because that non-polar part is elongated and can kind of just get out of the way. Right? Okay, so then let's compare that now to that tert butoxide fellow that was made down below. So if we look down here, we have the same thing. So here's our polar part, right? But now we've got this nonpolar part that's all crammed in together here, and it's just kind of in the way. So now when water comes in, this is making it repel out of the way, right? It's moving it essentially. So what we can say over on the side regarding this, and let's just continue and do that, and we'll just put these two summaries right next to each other, is that this is simply tougher to solvate, again, because now those non-polar parts are crowding the O- group. Okay, so that's the main idea. Now, there's an easy way to remember what the pKa's of these are, because in your textbook they're going to ask you to, in homework they're going to ask you to rank these things. So it's easy to remember. So primary, secondary, tertiary, 16, 17, 18. Right? Close enough. So there's some slight differences, but that's not going to matter if we're just making these ranking decisions. So it's an easy way to remember things. All right, so let's take a look here down below, and let's look at a special case down here. So there are some alcohols that tend to be more acidic for other reasons. So here we take a look at cyclohexanol, right? So it's got a pKa of about 17 to 18-ish or so, right? Somewhere in that range. It would make this alkoxide. And then down here we have phenol, and it makes this alkoxide. So look, why is the pK of this 10? What's the difference? Well, look at the stability. It's about the stability of the conjugate base. So this has solvation to deal with. So does this, but it has lots of resonance. So that stabilizes our conjugate base there, right? So remember, that's one of the factors that stabilizes conjugate bases. All right, now, the thing that we're going to see in the next chapter is we'll talk about how to oxidize alcohols. So when we start that conversation, we need to understand a little bit about oxidation states of the alcohols. So just looking up here above, we have heteroatoms. So heteroatoms are atoms of the nonmetal elements that are more electronegative than carbon and hydrogen. So it's basically these guys, okay? And for this chapter, we're really talking about making bonds to oxygen. So as we go from our left to the right here, you can see that we're gaining bonds to oxygen. We're also losing bonds to H. So it's the loss of bonds to hydrogen. That's oxidized. So going this direction, we're oxidizing. And then oxidation reduction works like this right there. They go in pairs. So over here, we're becoming more reduced. And here we have a loss of oxygen bonds or a gaining of H bonds. So in OChem and also in biochem, we use this quite frequently rather than going through and calculating oxidation numbers like we did in general chemistry. So it's a quick way to kind of find out rather quickly through inspection whether or not you're getting oxidized or reduced.